Good morning, everybody. Hope you're having a great day. Today we have a Codeforces round, as usual. This is Codeforces round 735. It's a Div 2 contest. Looks like it just started, so we'll jump right into it. All right, 5 problems, kind of a classic, old-fashioned style. Gotta love it. For problem A, we have n integers. Find the maximum value of some substring. Of the max of some range times the min of some range over all pairs LR in this range. So it's just going to be the biggest element squared. Right. I guess they're different. I see. So well, does making it bigger ever help? Probably not, right? If we have some range, suppose we consider increasing the size of the range by 1. Yeah, we only use one max. So pick the max and then pick the thing adjacent to it. So it's just it can be any range in the array, but really it's just any adjacent element, which makes it very easy to implement. All right, cool. Let's do that. We want the maximum, right? Yeah. So this is a at I times long a at I minus 1. We'll run it just to be safe, but it looks good. Yep, all right, cool. So then submit A. Oh, am I not registered? Oh, man. Well, right. So that's the solution to problem A. All right, problem B, Cobb. We have n integers. In an integer k, find the maximum value of I times j. Whoa, okay. Find the maximum value of I times j minus k times the OR of these two over all pairs I and j. What? Okay, can I register? When can I register? Is there late registration open? 6 minutes, okay. So find the maximum value of I times j minus k times ai or aj. So we're going to take two indices, multiply the indices together, then subtract k times the OR. This is not obvious. For a div 2b, this is, I don't even know what to do here. You want to look at some samples? So, k is 3. So you can do 1 times 2 minus 3. Yeah. They're probably both going to be pretty big, right? Yeah, so if you made these like n and n minus 1, how big is k? Oh, k is at most 100. Yeah, so you would, since k is small, like k is small, and this is gonna be, I don't know, not that big, maybe? I don't know. So it seems like maybe you'd move at most 100 left or something. You wouldn't move that far left from some element to find its leftmost. Or it's like a left pair that's ideal. Yeah, how far left would you want to move? Well, it might be really far, right? Is getting a bunch of solves? Getting a lot. I guess they're not getting that many. Is this just a wacky hard set? Man, this is a hard div 2B, I'm telling you. Holy cow. Yikes. It's brutal. Man, people are going to be complaining. Alright, you're given two integers, n and m. Find the max of the sequence, n XOR 0, n XOR 1, all the way to n XOR m. Oh, they're big though. Okay. Yeah, we can probably handle this one, I think. So, oh, multi-test case too. Okay. So we need, can we even do square root? You can maybe just barely. Or maybe not. Maybe you need faster. Well, it's not impossible, at least. It's approachable. Okay. So we have 0, well, let's do 3 digits. So this, let's say n is 1, 0, 1. Okay, so then we have XOR with 0, 0, 0, 0, 0, 1, 0, 1, 0, 1. Well, okay, so if m is less than n, then the answer is 0. Yeah. Okay, so now we know m is greater than n. So we know we go at least to this. So now we have 101. So now the question is, I guess, like, can we make a try out of this here? So what would that look like? We have this, then we have 1, 0, 1. So we can say if we're going from 0 all the way up to whatever, what's the first thing we don't hit? Yeah, so I guess we can just append zeros here if we need. So we have this try, and then this is the order we hit stuff in. And then I guess we want to see which of these do we hit. Yeah. So do we want some sort of range sum thing here where we're like, yeah, I think range sums might be the right answer. So here we're like, okay, do we hit this? Here we're like, how many of these do we hit? Here we're like, how many of these do we hit? Yeah, that seems appropriate. Can we register? Let's submit to A. Codeforces is insanely slow right now. We're really, asking a lot here. Come on, let's submit. Alright, so we got A. Presumably. We'll see. Okay. Yeah, B is tough. So this is like pay. So what's actually going on here is that we pay K dollars for each bit we have. Then we pay K dollars for each bit the other person has that we don't. And then we get the product of our indices. Oh, it's not each bit, it's for the OR, so each bit like times its usefulness. Okay, looks like we got A, which is good. We're having some issues here. This is tough, bro. This is really tough. I guess we'll move on to C. How about that? So, yeah, find the smallest non-negative integer that doesn't appear. So initially we'll have some big range of integers, and then we'll be like, I guess we need to know, do all of these appear? Do we have all of these things? Or are... Yeah, so we can ask like, are this to this less than... Okay. So this is an easy question to answer. If yes, we do it. Otherwise, we do something else. All right, so we can implement that, I think. So, yeah. Okay, so we read in T, the number of test cases, and then we read in N and M. So solve with 0, the bit is 31. I guess 30, 2 to the 30. Yeah. Okay. So we want to solve this. Alright, so here we go. Oh, we also need int m, I think. Int n and int m. So we need static Boolean. Well, we don't need to see if it's less than m. Okay, so yeah, here's what we need to do. Okay, so we can either add this bit or don't. So if we add, or if we don't add the bit, so if so we need to see if n has this bit. So if n and 2 to the bit is equal to 0, then don't add the bit comes first. Okay. Else. So now we just need to check if n has everything less than this being a 0. Everything where this is a 0. So if m is greater than or equal to, greater than, m is greater than or equal to, yeah, B, I don't know what they were thinking for B, to be honest. If m is greater than or equal to the min ants plus 2 to the bit minus 1, then solve min ants plus 1, or plus 2 to the bit, with bit plus 1 s in n and m. Otherwise, solve the min ants plus 1, or the min ants, the bit plus 1, same n and m. If the bit is equal to minus 1, then return 0, or return min ants. Okay, otherwise we need some other stuff. Okay, otherwise So here, adding the bit comes first because n has the bit. So now we check if everything, oh wait, if n has the bit comes first. Okay, so m has the bit. What does this mean? If we do have the bit, a number we might not hit with the max wouldn't have the bit. Well, it might have the bit. If we do have the bit, yeah, I don't know that I actually understand what I'm doing here. Okay, so either add this bit or don't. Okay, well, like, check if we have it. So n has the bit, or n doesn't have this bit. So what does that mean if we don't have it? That means we just like want to find the first thing bigger than m. Yeah, we know that everything, we know that for the things above us, we're at the first thing that isn't fully covered. Yeah. Okay, what if we do have the bit? If we do have the bit, we covered the later stuff first, so it's definitely the stuff without the bit. It's going to be not hit. This is so sketchy. I don't think that's right. -1. Yeah, let's think about that. So what does this look like for 2, 5? 2 XOR, yeah, so it's, so what does this look like? So we have this 1 1, and then we have 0. So we hit 1, 2, 3, 4, and then 5 over here. So this part is almost certainly the part of it that's wrong. We're saying if we don't have this bit, check if we can add everything. So there's something we don't hit in this range. If m is greater than or equal to the min answer plus this, greater than, yeah. That means we hit everything in the range. Do we want to subtract min ants from this? Probably, yeah. So in this case, m yeah, the first thing you don't hit is going to be in this half here. Okay, should have done that a while ago. So 5, let's say 2, 4. Okay. 2, 4. So 4 XOR 2 is 6. We don't hit that. Oh, this is more like a digit descent DP. Oh my goodness, Rainbow going off. Well done, sir. Okay. Let's do B here. So suppose we know what the OR is. Then the question is, what are the two rightmost things? Yeah. So that's one solution. We can do that. Yeah, that works. So we've got this big array, and then we're like everything. Well, initially we also have like all these values. So we're like everything with a value less than, do it. Oh, I guess we can just well, if we brute force, okay, so we say the OR either has this bit or it doesn't. But there are a lot of ORs. There are 10 to the 5th ORs that it can be. So we can't brute force the OR. We have to abuse the fact k is small. So we're going for like an n times k solution. What if we did the rightmost and the second rightmost for each OR value? Yeah, okay. So there's this. The bit count of n no, integer dot highest one bit, integer dot number of trailing zeros of integer dot highest one bit of n plus 1 maybe. That many bits. Okay, literate size n. So then we need int array biggest index with submask, or biggest index of submask. New int array 2 to the n bits. Fill it with -1. Then for each thing up to n bits, we say biggest index of submask at I. No, it's not true. So for int I equals 0, less than n plus plus. Biggest index of submask at I. Equals, or at 8i equals I, up to n bits. To the n bits. Okay, this is baked into submask. This one looks good. Very good. Now we have the biggest index of the submask. But really we need the biggest pair of indices. Yeah. Alright, so let's make this a p array. Equals new p, So it'll be this and then minus 1 equals, this will be combine this one with this. Is it that easy? Might be. Okay. So now, oh, we also need to read in k, right? Yeah. So then, long ants equals long dot min value. This out ants. Then 4 int or equals 0 or is less than 2 to the n bits or plus plus. Which equals math.max of or sorry, of the answer, or times minus k plus, this will be a long, plus p dot a, oh, this is just a p. So if p dot a is not equal, or is greater than or equal to 0, and p dot b greater than or equal to 0, then we could use this. P dot a times long p dot b. All right. Oh, yeah. I can count to 4. Oh, I guess these are both 1 indexed, but okay. Okay, so the or of 1 should be 1, 2. Okay, this is combine. Minus 1, okay. And then 12, looking good. was not easy. Maybe I massively overcomplicated it, but we'll see. May not have even gotten it right. Okay. It's hard. It was hard. It's a very hard div 2b. Brain Boy winning the contest. That is actually just legendary. I'm telling you. Let's go. Alright. We've got two integers. Find the max of some sequence. Yeah, so... Okay. Let's actually solve this problem first, because I don't think it's that bad. Check, is it like the first X numbers? So it's not monotonic is the thing. Like, you can have 7 but not have 2. The problem though is if we, or like the convenient part is if we look at it as like binary digits, then you can check, do you have everything in this binary digit? So, yeah, if n is like, well, let's look at this 3-5 part maybe. So we have we can get all of these because they're less than it. Yeah. So it's, can we go left? And then we also have how many? Alright, so we're almost there. Here we always go left, but this is not right. So this part is M. Yeah. This is M minus to the bit. To avoid any wrong answers, just in case. Looks good. All right. Good. Should be able to get C then. Okay, on to D. You're given an integer n. Find any string of length n consisting only of English letters. Sounds like we got it. Such that each non-empty substring of S occurs in S an odd number of times. Try one more time. Find any string S of length n of English lowercase letters, such that for each non-empty substring, it occurs an odd number of times. If there are multiple such strings output any, it can be shown that such string always exists under the given constraints. What? Oh, this is kind of cool. So it's like, just do it. All right, well, let's just write a checker here. Thank you, by the way, for not guaranteeing this exists. I just want to say, well done, authors. Appreciate it. Yeah, okay. Well, we should read E, just in case. You have a tree with n nodes. As a reminder, a tree is connected, undirected graph without cycles. Let this be a sequence of integers. Perform the following operation n times. Select an unerased node U. Assign U equal to the number of unerased nodes adjacent to U. Then erase node U along with the edges that have it as an endpoint. For each k, find the number of different subsequences that follow the following conditions. It is possible to obtain an array A. Are we given an array A? It's possible to obtain an array A by performing the aforementioned operations exactly n times in some order. The GCD of these things is equal to k. Got it. Got it. Can it ever be bigger than 2? Can you ever do 3? Yeah, maybe. You have a star graph of size 3? So other than star graphs, though, you run into problems. This might not be that hard. It might be easier than it seems. Because it sounds like really difficult to make any test data for this. I'm not sure. D, on the other hand, is a big mystery. So let's do this. So int times equals 0. Oh, we did this already. Int I equals 0. I is less than s dot length. That's not true. The character A appears an even number of times. Okay. So you have ABA, CA. An odd number of times, huh? Okay, so I guess what do we have? So we can do A, right? We can do AB. We can do, can't do AAA. Can't do ABA. So we have to do, I guess, like AC or ABC. And then we can do that obviously doesn't work. A, B, C. Yeah, so we can't have 2 A's if we have 3 A's. What's wrong with this? How does this work? So then what's the next length? So we need 5 characters. So this works. We can also do ABAC. Huh, that works. So why is that? Three appears once, 2 appears 3 times. Okay, interesting. Oh wait, what is 3, 4? This works. Cool. So we can get 3 plus 4. We can get well, that's awesome. Okay, and then we can just append to that, right? So we can add 2 characters, or we can just get the C. Okay, so we can get B. Okay, let's try this again. We've got B. We have BC. We have B. Oh, I guess this is BA. Then we have BAC, and A, yeah. Yep, okay. Do I know why this works? No, but it makes sense, kind of. Yeah, it kind of makes sense. Okay, let's just verify. That's a fun problem. I feel very smart having solved it. Okay. Is this multi-test case or no? Yeah. Okay, so then how many things do we want? So this is 0, this is 0, or this is, I guess, well, okay. If n equals 1, X out B. We need print writer for sure. Okay, if n isn't 1, then, so this is 0, this is 0, this is 1, this is 1, okay. Int start will be n. This is 2, 3, so n over 2 minus 1. Okay, 4 int I equals 0, less than start, I plus plus. Out dot print A, out dot print B, print A, out dot print line, and then if start, or if n mod 2 is equal to 0, out dot print line C. So 3, this is not 3 characters. One, two, three, 4. All right. Yeah, that was definitely easier than B. That's for sure. Oh man. Okay. Yeah. So, I guess proving it? I don't know. I don't know if it, well, like, you can make a proof though. Yeah, you can make a proof. Yeah. Okay. I have a proof. It's just like, I didn't come at it from the proof. I came at it from a, hey, this thing works, and then like, oh, look at that. Like, I noticed, hey, that works. Cool, I bet this will work too, and then it does, and it's like, okay, then awesome. All right, problem E. Let's solve this set here. So we have a tree with n nodes. A tree is an undirected graph, so we're going to delete nodes from this tree. We need for each k, that's a lot of things. Okay, so we need the GCD of the elements to be k. So, yeah, we've got this wacky constraint over here. You got this wacky constraint that, like, if you've got something like this ever in the tree, you have to delete one of these before the other. Yeah. So the GCD can be at most the degree of this. Because one of them's got to get deleted first. So, yeah, it's like, I don't know, whatever that counts for. So we know the max the answer can be. Min of the degree across every edge. legs are sore. Yeah. Min degree. So for each one of those, we have to pick, well, we pick some number less than it. So like, what's the min of the max degree? This is 0, 4, this is 0, 4, this is 0, 4, this is 0, 4. We get the 4 and then we get all these zeros. Let's say we want the answer to not be 1. When is the answer not 1? So it's not here. What if we have like a less, what if we have this tree? Is there any way to not have a 1 in this? We can take this? No. Right? It's always going to be 1. If we take this, it's a 2. This is 0, so that's fine, but now one of these is a 1. Okay. So what if we have this? Then we can get a 2, and then a 2, and then yeah. Is there any other way of getting a 2? We can't get a 3. So this can get a 2, or it can get a 1 in a lot of ways. Is there ever a situation in which you can have multiple possible answers? That aren't 1. Like you can, a lot of times you can have 1. Can you ever have something else? Oh yeah, maybe. So this is 2, let's make this 4. Okay, so here we can get 3. Well, can we get 2 still? Yeah, we can get 2 or 3. So to get 2, you would take the 4, and then 2. To get 3, you would take a 3 and then a 3. So yeah, there are multiple ways of doing it. There's only one way for each of them though. So it's still not really that exciting. We also have the constraint that, okay, no leaves can be taken first. Yeah, so all the leaves are going to be zeros. And the order in which we take the leaves is irrelevant. but they have to come at the... Ooh, do they? They don't have to come at the end. Yeah, they don't have to come at the end. Okay, so... It's like, take something, subtract 1 from all its neighbors. And then GCD yourself with the answer. Okay. So parity-wise, if we take this thing first, yeah, okay, so I think there's only one way of doing it. If we know which thing we're taking first, like let's say we're taking this first. I think we know what this degree is going to be. Modulo 2 at least. Or maybe not. Yeah, we do. Yeah, we do. Here's why. We could take A. So, okay, so let's say this is A. This is B, and this is C. We could do A, B, C, for instance. And then we can do C, B, A, maybe. The problem is, here A has the same parity of degrees. So if our value under mod is like mod 2, then A is the same in both of these cases. But the issue is that B and C now aren't. So 0 plus 1 plus 1, let's make this 0, and then make this plus 2 maybe. So we remove this, remove this, remove this, remove this, remove this. So we can brute force the GCD. And And then we know what the GCD is, we know what everyone's value is. That still doesn't work though. Or does it? Does it? Maybe it does. What if we have a two-colored thing? So we can have like a 0, 1, 0, 1, 0. So in this case, we can do this, 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 and then end here. Yeah, so you can do this in different ways. So you can do, one way of doing this is you can do 1, 2, like 3, 4. Another way, well, 3, 4, 5, I guess. No. So this is going to get subtracted from, so this is impossible. Why is this impossible? Because this is a 0. Yeah. Okay, so this isn't possible. Is this, okay, is it ever, this is a 0, and this is a 1. This thing has to be, yeah, if this is a 0, we have to start here. Not necessarily. We could have two neighbors. Yeah, so in this case we've got 1, 2, 3. 4, 5. Okay. Yeah, so let's say we brute force what the GCD is. And we know the direction of every edge. Yeah, that's smart. Let's consider that. The direction of every... Oh, man, I should have thought about that ages ago. Yes. Okay. If we direct the edges... Oh, man, how do I not see this? Okay. You direct the edges. Let's go. That's the solution. Ladies and gentlemen, direct the edges. Okay. Yeah. Yeah. The edge directions are what's important here. So this means yes. Okay. Got it. So you direct the edges. That means we pick this before this. Okay. And now we want to direct the edges in such a way where it works. So here, what does this mean? We need 0 edges towards this. We need 2 edges towards this. No, 2 edges towards this. 1 edge towards this. And one edge towards this. Yeah. So if we know the GCD, we can do this from how big is n? 3 times 10 to the 5th. So how many factors can n have? Or we want the sum of, there are probably not many that work, right? Like 0 will work, 1 will work. Bigger stuff, we'll figure that out later. Okay, we direct edges. With like a BFS, maybe? Yeah, so if we have a 0, we know it's gotta be a 0, we direct the edge away. So now we have all of these directed edges. And now it's like, how many times does it work? Which is more difficult. Yeah, that's kind of hard. So for how many GCDs is this going to actually end up working, I guess, is one question. So we need each edge, probably at most cube root, each edge gets added to one of two things. So the sum of all of these numbers, that are added is the sum of edges. Yeah. So it's got to be a factor of that. Otherwise it's 0. Sanity check me. Okay. This has 2 edges, so it's got to be a factor of 2. 1 or 2. Three ways for a GCD of 1. Oh wait, is this 2 on 0? Three ways is GCD of 0 of 1. 1 with a GCD of 2. Oh, 0 with GCD of 3. Yeah, okay. Yes, okay, so it's got to be a factor of that. So this happens cube root n. Now we direct the edges, so now it's how many ways are there, how many top sorts of a directed tree? Yep, right? Yes, how many top sorts? Of a directed tree. Am I gonna have time to finish? Maybe. Okay, so we've got some stuff here. So we pick an edge. How many things need to come before it? You need to come before it if you can reach it, right? Yes. You need to come after it if we can reach you. man, that's kind of messy. So this kind of looks like this. So this one and this one, followed by this. This is what the graph looks like. How many ways are there of doing this? So we can handle a tree easily. This part's easy. And then these two are independent. Are they independent? Kind of. They both have to be after this, is the problem. So if you have some node, you can do this part, you can do this part, and then you can shuffle. L, R, and then shuffle. What if somebody else can reach them then? Like, when you start shuffling these, it screws up this guy. Suppose a DAG is a forest of paths. Okay, that's easy. Yeah, okay, well, I want of a tree. A directed tree. Yeah, this is what I want. For a directed tree with a fixed root. Well, this is a fixed root. Yeah, I don't think this is helpful. Yeah. The number of top sorts of a directed tree. It's interesting here. So, well, are there any constraints on these directions? Not really. They're not strong ones, I don't think. Well, maybe they are. No. Like, to some degree, they're like never things to a leaf, or they're always to a leaf. Like, I don't think this exact problem would ever show up. But I think if you get rid of the leaves, I think you can make anything you want. Are we always going to have a node like this? I think so. Yeah, you'll always have one of these nodes. Is that true? No. We don't have one of those nodes. So in this case, we can do, yeah, it's, you've got some constraints, but they're all kind of wacky. Maybe top sorts of a directed tree is just hard. Maybe this isn't a fair simplification. Maybe it's easier than that. Here we go. Let's root the tree at some array. This be the number of topological sorts of the subtree at I. So it is possible. so we can't do n squared, but what is this saying? Number of topological sorts such that the subtree rooted at I and the ith node is placed at this position. Let's calculate dpij is the number of topological sorts of the subtree rooted at the ith node such that the ith node is placed at position j. I think this is the old version. Yeah, if the tree is ordered in... Well, this is probably hard. Yeah. It's in a DAG. DAG we've learned is MP complete. I don't know how to do this. How do you find the number of top sorts of a directed tree? It's tough because like it's not independent anymore. Like you have weirds, like it's just weird. Like where this thing is affects where this can be, right? Yeah. Like this thing can be in either of the first two spots. Where it is determines where these ones can be. And then this one has to be, well, this can be in some other spot, but it's just messy. Maybe it's like some centroid decomp thing or something. Yeah, okay. So I don't know. I can give a general idea for this, or for all of the problems, but I don't have a real solution to E. That would be nice to know how to do, for sure. Yeah, there's some homework for me. Okay, I guess we'll go over solutions here real quick. So here's the idea for each of the problems. Here we go. All right. Okay, problem A. So you have n integers, and you're gonna find some subarray. Then you're gonna take the maximum in that range, the minimum of the range, and multiply them together. And you want that value to be as big as possible. So one way of thinking about this is, I guess we'll do an example really quickly. Maybe the array is 3, 2, 3, 1. That was a good array. So here, if we look at, let's say we were to pick this range here. The maximum of this range is 3, the minimum is 2, and then we get the result of 6, which is 3 times 2. And this is the best one you can pick for this array. So let's look at this for a bit. One thing to notice here is like we're going to pick some range. We can think about it as we're going to pick the range because we want some maximum in that range. And then as a penalty for a range being big, we're going to have to accept some small minimum. So like we want to keep our range small. That's beneficial to us. Because having a small range means that there are fewer choices for this minimum. In other words, let's say we picked this range to have this as our maximum. Once we've extended the range to be too long, that satisfies the requirement that the size of the range is at least 2. We're not going to gain anything else by making the range longer. It might make our answer worse, but it's not going to make it better. So it would be better for us, or at least no worse, to pick this range, because then this answer will be at least just as good. So there's the greedy argument that if your range is size 3 or more, you should make it 1 shorter. You're not allowed to pick just the biggest number squared. If you were, the problem would be too easy, I guess. But yeah, if you were, that would be the best range. But since your range has to be at least size 2, then you do this. So once you know that that's the problem, there aren't that many candidates you have to try, and the problem gets really easy. You just have to try every pair. So you just try each pair of numbers. Whichever one of those has the biggest product is your answer. Code for that is super simple. Uh-oh, what have I done? Code for that just looks like this. So we read in our array, we try every pair, and then whichever one is the biggest is our answer. Cool, that's problem A. Problem B, cob. So we have an array of n integers and an integer k. We want to find the maximum value of this thing. Now this is a bit difficult to understand. What this is it's like the product of 2 indices. So you're going to pick 2 indices. The value you get is the product of those indices times some multiplier of the OR of their values. Yeah, the bitwise OR. There are probably a lot of ways of handling this problem. One thing you can notice is that k is small. My solution doesn't use that at all. So there's probably something a little bit easier that takes advantage of that and notices that if these indices are really big, then k is not going to hurt you that much. So yeah, that's probably something. But a different thing that you can do, maybe I'll solve a harder version of this problem here. Let's say we didn't have this bound on k. Let's say k was up to n. We can actually solve this in a general case. So what we're doing is we're saying, let's say we have a bunch of numbers. We're going to pick 2 of them. And then our cost here is going to be the product of the indices minus the OR of the values times some constant. It can be up to 10 to the 9th maybe. If that's the case, we can say the complicated part of evaluating this score is the OR of these 2 numbers. It's like very difficult to handle. So we know all of the numbers themselves are up to n. That is something that I'd use. So since the numbers are all small, we know they don't get very big, which means the OR of 2 numbers, so like a or b, is less than or equal to 2 times n. That's a good, helpful characteristic. I guess it's less than 2 times n always. Got to get the crazy optimizations in here. So we know this is the case. We can abuse this. So let's say we know what this is, right? Let's say we know this OR value. That means we're allowed to pick any elements that are a submask of whatever this OR value is. We're always going to pick the rightmost 2 elements because we want the biggest product. So we want to multiply the biggest 2 numbers together. Since all the numbers are positive, that'll give us the biggest answer. So we just want to know what are the rightmost two elements that are a submask of x, of some x. And we want to know this for every x. Now, this is actually a really common problem. So this is something that I've seen before. If you've done enough Codeforces problems, or you've seen something like this, saying like, let's find some aggregate over all of the submasks of this number. This is a common thing. So one great blog that you should take a look at, it's called SOSDP, which stands for sum over subset. So you want to know for all subsets of this element, what's the sum of all of them? Instead of sum, you can also do like max or min or GCD or something. So in this case, I just did the max and then the second max. And that's the idea. So the sum over subset DP, you should read and understand how it works because it's really helpful to know that. But at the end, you're like, okay, you just have this code and then you understand this code. So it's like 6 lines or something. Once you have that, you can just plug in this stuff here. Wait, where is it? Yeah. So here's the DP part. And this is basically the same thing. The only difference here is instead of adding, I'm using this combine method, which is like find the 2 biggest values. So find the biggest and the second biggest of these 2 subsets. The way this works is a little bit difficult to explain if you're not familiar with it, but the general idea is that like if you have a 1 here in your submask, that could involve either having come from a 0 in this bit or from a 1 in this bit. So if we process these bits in order of like smallest bit to biggest bit, then we can say like, okay, if you have a 0 and a 1, combine them together in this place in memory. And you can hit it, like the way the code works, it hits it in just the right order. So everything's iterative, it's super clean, and then you can combine them all into one array, and it works really nicely. But yeah, that's the idea. So the TLDR for this problem is we want to say what is the biggest index that is a submask, whose value is a submask of x, and then also what's the second biggest index whose value is a submask of x. And then we solve that here without any abusing of k. So I thought this was a hard problem. I would have put this as like a div1. This seems div1 to me. It seems maybe div1a, probably div1b. But it's possible that k being small makes an easier solution. I guess 3,000 people are solving it, so... Or maybe I'm just stupid. Who knows? It's always possible. Could have woken up on the wrong side of bed today. So yeah, who knows? Okay. All right, problem C. So that's B. Problem C. Yeah, what was C? C was this mex thing. So we have some integer n and then some other integer m. We want to know the mex of n XOR 0, n XOR 1, n XOR 2, all the way up to n XOR m. So what does that look like? Well, there is an interesting way of us looking at this problem, which I think makes it easier to solve. And in particular, what I mean is let's change the way that we count numbers. So let's say you might be familiar with a trie. All a trie is it's just a tree, but with like zeros and ones on the edges. So maybe I'll just draw a trie here. So the idea behind this trie is if you go left, it's a 0. If you go right, it's a 1. And now each of these root nodes on the bottom represents some binary string. So this is 0, 0. This is, you take a 0 and then a 1. This you take a 1 and then you take a 0. So it's 1, 0. This is 1, 1. And this will give us all the binary strings at the bottom. So this is an interesting way of thinking about problems with this sort of characteristic, like this bitwise stuff, because like at each step you take a 0 or a 1, and then things are ordered from left to right, from smallest to biggest. So a lot of times this is a helpful way of looking at it. This is how I looked at this problem, and I think it was helpful for me, so I'll try and use this to explain it. So the idea here is, in general, if you're counting from smallest to biggest, at some node, first you go left, you process everything in this subtree with some BFS or DFS, probably DFS actually, and then after you do that, you go right, and then you process everything in this subtree. And that'll hit things in this order, which is the order you want. However, if you're XORing this with some other number, if this has a 1 bit here, when you would place a 0, you would go to the right subtree first. So you go to the right subtree, do everything in the right subtree, and then you'd go to the left subtree. So we're gonna just kind of like walk through this try and then just see what is the first thing we wouldn't hit. And it's that easy. So basically we want to say, okay, let's make a bigger try here so it's a bit more, I can do a bit more thorough of an example. What on earth? Okay, so let's say the try looks like this. We'll do 3 layers. Okay, and let's say n equals 3, and then m equals 4. So in particular, what we're going to do is we're going to XOR. So we're going to do 3 XOR 0, 3 XOR 1, 3 XOR 2, 3 XOR 3, and then 3 XOR 4. Those are the numbers we're going to hit. So in particular, the numbers we end up hitting are in this order. So first we hit 3 XOR 0, which is 0, 1, 2. So we hit this, then we hit this, then we hit this, then we hit this, then we hit this, 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 this. So it's that order. I changed my mind. Let's make n, well yeah, 3 is fine. No. Let's do 5 and 6. Okay. This will be more interesting, I think, or it'll look better. So we do 5 XOR 0, 5 XOR 1, 5 XOR 2, XOR 3, XOR 4, 5 XOR 5, and then 5 XOR 6. Okay, what order do we hit them in? So first we hit 5. So 5 is this one. We hit this one, then we hit this one. 5 XOR 2 is 7, so that would be this. Then we hit this. Then we hit 5 XOR 3. Oh, we did that already. 5 XOR 4 is this, this, and then we hit this, this. Okay, so that's the order we end up hitting everything in. However, we don't hit the last 2. So the first thing we don't hit is this, I think. No, yes, it's this. But I think this is the answer we're looking for, but we'll get there in a minute. So when you're walking through the tree normally, like I mentioned earlier, what you want to do is, in general, you follow the left path and then you follow the right path. The problem is we're XORing with 5. So when we do that, really, since 5 has a 1-bit here, if you follow 5 through this try, you go right and then you go left, because it's 5 in binary is 1, 0, 1. Oops, you can't see that, but 5 in binary is 1, 0, 1. So you go like left, right, left, and this is 1, 0, 1 in binary. So this is 5. Which means the paths that we'll take by default are this one first, and then we take this one, and then we take this first, like we normally would, then we take this one, and then we go right first. So these are all of the paths that we would take in the first order we would take them, where like the solid is the first line and dotted is the second. So this is what helped me visualize it. So now what we want to do is say, let's start from the root and let's find what is like the first thing we don't hit. So initially, we're like, okay, we know there's some number here that we don't hit. We know there's some number less than 8 we don't hit. Okay, is it going to be in the left half or the right half? Well, the first 4 numbers we hit are going to be in this half, because the first 4 numbers are all going to be to the right. Which means we're going to have empty space over here, because we hit 6 numbers, so there are going to be 2 we hit and then 2 we miss. So the answer is going to be in here. However, when we go into this subtree, now we're looking at, instead of hitting all of the numbers, or instead of hitting 6 numbers, we only hit 2 of them. because 4 of our turns were spent over in this subtree. So now we know we hit two elements in this subtree. What are the first 2 we hit? Well, we start by going left. So the question is, okay, we want to find the first element we don't hit. The first 2 elements go to the left, the next 2 will go to the right. If we hit 2 elements total, will we hit anything in the left? In this case, we will. We'll hit all of the things in the left, and then we won't hit anything in the right. So we'll be like, okay, everything in the left is hit, so we can skip that part, and now we can recurse to this half of the try. Because we know we've hit all 4 of these eventually, and then we know we hit everything here. In this case, we can also subtract 2 from the number of things we've used, because we've used 2 of them in the subtree we hit first, so we subtract 2. Now we're in this subtree here. So in this subtree, the question is, what is the first thing we don't hit? And we hit 0 things, so it's going to be the first thing. But the question is, do we hit everything in the left subtree? And the answer is no, we don't, because we have 0 things to hit left. So we go to the left subtree, then we end up here, and now we know our answer is what we thought it was earlier, which is this. So that's me walking through an example. I think that's a good example for how to solve this in general. And then the runtime here is going to be order log n, log 10 to the 9. So this should be plenty fast enough. Here is what that looks like. So we just have this recursive method here, and then we're good. Yeah. So I guess my code's a little bit messy, because I'm like, this M is not the right way of doing it. Instead, you should, this is, the code's not great. The way I explain it is better. You should keep track of how many things do you still have to delete in the subtree, rather than whatever I was taking care of here. Most of this was just verified by brute force. I probably would have recoded it if I didn't know that it was right, because it's messy and kind of annoying. It technically works, but it's just a mess. Yeah, so so don't do this. There are better ways of doing it, but this is good enough, I guess. All right, last one is problem D. Or actually, there's D and E, so we'll talk about D here. So we have this string, and we want to make it so that every substring occurs an odd number of times. This was a super cool problem, by the way. Let's look at what a bunch of A's looks like. So if we have 4 A's, there are 4 different substrings that occur. There's A, AA, AAA, and then AAAA. This one obviously occurs once. This occurs twice, so it occurs here and here. This one occurs 3 times, and this one occurs 4 times. So if we look at which parts occur an odd number of times, we have this and we have this. Now let's do a similar thing, but for length 5. We have a 5th A here. Now we have this one here. I'll make a separate category for it, so this is 0. This will occur once, this occurs twice, this occurs 3 times, this occurs 4 times, this occurs 5 times. Which means that we have the opposite pair occurs an odd number of times. If we add these 2 together, in total, this will occur, 9 times, but this is odd. So we have a square here. This will occur 7 times, which is odd. This will occur an even plus an odd, which is odd. And every substring occurs an odd number of times. If we have 4 A's, some separator, and then 5 A's. Yeah, I think that's helpful. Okay. Now the question is, how do we make a good separator here? If you just use a B, that'll work. So we have 4 A's, and then a B, and then 5 A's. In this case, if your substring includes a B, it only occurs once. So if we have this substring here, 2 A's, a B, and two more A's, there's only 1 B in the array, so I can tell you exactly where that substring occurs. It's only in that position. If it doesn't include a B, then it's one of these 5, and we just showed that each one of them occurs an odd number of times. So this is basically the solution to the problem. The idea here, the important thing to notice, is that it doesn't matter how many A's you have. So you can have 100 A's, a B, and then 101 A's. And that will give you a string that's length 100 plus 101 plus 1. And this will solve for any even length string. This will give you the answer. If you want an odd length string, you can just add a C. Or you can put the C in here. Right? You can do a bunch of A's, B, C, and then a bunch of A's. And that works too. So yeah, it's that easy. You just have to see it, or write a brute forcer, or something like that, and that'll give you the solution. The code is pretty trivial. So here's the code. For me, I thought it was helpful to have a checker, so I made this checker to like sanity check something. And then the way I found this is I was just like trying some different stuff. I'm like, okay, let's come up with some answers. And then I noticed that that this worked. This is like, oh wow, so you have one A, you've got two A's, you got three A's, and then you have one more A. But like these two ones kind of cancel each other out, so you kind of have this, and then it's like, oh, well, does this work? And it does, and it's like, oh yeah, obviously it works. And then it's like, okay, then you can do this. So that was my path to figuring it out, because just saying, look, this solution works is maybe not a super helpful way of showing someone how to solve the problem. But yeah, this is how I discovered it. I had the brute forcer, tried some stuff, and then found it. And this is a solution. You also have to special case when n equals 1, because I don't handle that very well. But yeah. You can also, I guess it goes without mentioning, if n is less than 26, you can just do a bunch of unique characters. And that works too. But that's not helpful for the general case, because in that n is all big. Okay, awesome. So yeah, that's problem D. The last one is problem E, and I can give you some logic here. It's not like a full solution, but it might be a little helpful. So in problem E, we have a tree. Sorry, you got an undirected tree. Maybe it looks like this. And what you're going to do is make an array, but basically you're just going to delete some nodes in some order. So maybe you delete like this node, or maybe you delete, let's do this. You delete this node first, then this node, then this node, then this node, then this node. When you delete a node, you write down what its degree was when it was deleted. So here the degree was 2, and then we got rid of this. Then this degree was 2, so we got rid of this, and then this is 0, 0, 0 when you got rid of these 3. So the GCD of these numbers is equal to 2. The question is, for each possible GCD, how many orderings are there of deleting the numbers to get that GCD? So in this case, if you want a GCD of 2, you have to delete this first, and then you can delete this, and then you can delete any 3 of these leaves. You can also delete this leaf before you delete this element. So there's that. So you got some different orderings. But the key thing to notice here is that what really matters is the direction of each edge. So we can direct each of our edges in a pretty clear way, assuming we know what the GCD is. So yeah, okay, let's do that. So instead of like deleting the nodes, let's look at directing the edges. We'll look at the same tree, and we'll say we want a GCD to be 2. So we know for this node here, it's got 2 options. Either this node has a GCD of 1, or it has a GCD of 2. We can't, or sorry, GCD of 0 or of 1. If the GCD is 1, then we're going to ruin the GCD of 2. It can't possibly be 2. So we need to direct the edge this way, so that we don't make ourselves 1. Same thing with this, we need this edge directed here. Now for this node, it's got this edge here. So we know the GCD for this node can be 2, or the number for this node can be 2 or 3. We obviously want it to be 2 if the end GCD is 2, so we'll direct this way. And then this node, well, we have one edge left. The GCD can be 1 or it can be 2. This number can be 1 or 2. So we want it to be 2 because 2 is divisible by 2, so we'll direct this in this direction. So we can direct all of the edges with a top sort if we know the GCD. The other thing to keep in mind is the total number that we're adding across all of these numbers in the entire array is going to be the number of edges, because each edge adds 1 to one index in the array. So the only possible GCDs at the end of this are things which are a factor of the number of edges. they're most cube root of n factors of some number, or like roughly it's about cube root of n, worst case. So we can bound that pretty reasonably. And then we know we have cube root n factors of some number. So we can be like, okay, we have not that many things we need to check. For each thing we want to check, we can direct all of the edges. We can do this with some top sort, so we just keep removing leaves one by one, and we can do that in linear time, so this is order n. And then when we're done with that, we just have to say, how many ways are there of sorting a tree topologically with edges directed in this direction? That's the part that I don't quite have figured out. And it's possible that that's impossible. I don't think it's impossible. I think it's doable. But like the reason I say it might be impossible and this problem might still have a solution is because this tree has specific characteristics that a general tree doesn't, because of the way we're generating it. So we almost never have edges going towards the leaves. Like that's one thing. But if you remove all of the leaves, I think you can have basically any tree you want. So I don't think it matters. I think it's basically a general tree. I think whatever approach you would use for this could solve a general tree of half the size. So yeah. I'm not. Yeah, I think you can basically have the tree be however you want. So yeah, so the question is, how do you top sort a tree? A directed tree that isn't necessarily rooted. In this case, the tree is rooted, but you can have other trees that are more complicated. Let me show you an example of that so you recognize why this is difficult. So in this case, you can have something that looks like this, right? This is technically a tree. There are no cycles, but it doesn't have a single root, right? There's no one node that can reach everything. You've got like two paths which merge and then separate. So there is a tree structure here, but it's like kind of difficult. If there was just a clean root, then this would be easy to do. But in this case, there isn't. You can also have something like this Z shape, which is also a bit messy, and I don't know exactly how to handle it. Yeah. All right, so that's the general idea behind this round. Looks like system tests are going pretty well. No one seems to be failing. Yeah. Hopefully the solutions were kind of helpful. I guess let me know if there's anything that you think I could have explained better. And hope you did well in the contest, especially if it was rated for you. Okay, that's all for me. Have a great day, and I'll see you in the next one. Goodbye.